My last topic is NMR. Spartan'18 differs in two places. It differs in that we continue to improve the parameterization scheme. We have a scheme which corrects the calculations, and we've continued to make improvements on that. That scheme is done in the interface, and so anything that's run previously can benefit from those improvements. The second thing we've done is we've combined this with the conformational search logic to bring into practical means NMR predictions on flexible objects. Without doing anything, if you use the omega XD functional with a small base set, so something that's practical, you get an error looking at literally 10 or 20,000 chemical shifts of, this is carbon, of molecules that are essentially rigid, so I don't want to worry about flexibility. You get an error of something like 3.5 ppm. Other functionals, we've looked at B3 lip, are a little worse than that. They're maybe 4 or 5 ppm. But either way, they're not really good enough to be useful, at least in my opinion. If you go to bigger basis sets, and we've gone as large as the one listed there, you get different results, but they're not any better. And so what it's telling you is that, at least at this level of theory, at density functional theory, which has not been developed for NMR, it's been developed for essentially energy predictions, you really can't get inside a number of, say, 3.5 ppm. I would contend that isn't suitable. My target has always been something like 2 ppm, which is a number that I have sort of formed the opinion that's close to the solvent dependence of at least carbon shifts. If you show 3.5 ppm on a plot, this is a series of a small number of rigid natural products. It doesn't look so bad, except if you were to zoom in on that, you would see that you have deviations of 7 or 8 ppm on there. It's really not very good. You'll also see that the aliphatic region is superior to the olefinic aromatic regions, partially because they're just bigger numbers, but you're seeing larger shifts. Several years ago, we developed a correction scheme. We keep modifying it. The present version is the following one. It's very simple. It says that you calculate a chemical shift. You take that chemical shift, and the first thing you do is scale it. You saw there was a systematic error there. You scale it, and then you add a small term. It's actually rather small, which depends on the who's bonded. So you're summing over who's bonded. So you're counting, how many neighbors do I have, and constants of what the atom is that's bonded: carbon, nitrogen, oxygen. We've only parameterized for 8 or 9 elements, and a bond distance. And so it's a power series and a bond distance. This comes up with something of the order of 45 parameters, which is a big number, except you've got 20, 30,000 data points to fit it to. So you've got plenty of data points. So it's statistically meaningful. And it's intuitive. It's who I'm connected to and how far away they are. If you do that, the plot is significantly better. I should really expand the axes. It's much tighter. You've gotten rid of the systematic error, that's the scale, but you've also cleaned up things. And those are probably incorrect experiments at that point. To give you an example of the sort of quality there, just a simple molecule, it's strychnine. These are differences between calculated and experimental, and you're at or below the sort of 2 ppm goal. I picked strychnine because it's a little bit big and it's completely rigid, so you can see that's basically close to the target. What can you use it for? Well, for example, if you wanted to know menthol is well defined, but there are forgetting absolute configuration, there are 4 isomers. Depending on, fix that one, you've got 2 stereocenters independent of that. Which one is it? Well, you could look at this and decide which one is better, or now you could introduce this very pretty tool called DP4, and again, I have to do this a little bit by hand now. You could basically say, I'm going to calculate the NMR of all 4 of these, having worried about what their conformers are. So I'm going to calculate the NMR of all 4 of these, and I'm going to put them into this statistical tool called DP4. And essentially what it's doing is it's trying to select the least bad of the set. And it's really statistics. It's not a quantum mechanical method. But what it really does in this case, it's saying that one, the RRS configuration, referring to here, is 100%. You'd get a table like this. And what it would tell you is that one of them was, I'm 100% certain. Now, the advantage of this scheme is that the quantum mechanical model underneath doesn't have to be very good, because it's not asking the question whether the 100% is actually a good match. It's saying it's the best match of the ones you've given me. The disadvantage of the scheme is exactly the same, because you're deceiving yourself. You're saying, gee, that's 100%, it's got to be that. I don't know. It's better than the other one. Another example is thujone. There are two stereoisomers of it. They're both known. If you think you've isolated one of them, again, think more interesting molecule. If you think you've isolated which one, what you do is you do calculations on both and simply compare it to your measurement. And I've shown that here. If you do a calculation on the S absolute here, in enantiomer, you'd get one result. If you do a calculation of the R, you get the opposite result. So you can, in fact, now separate stereoisomers. The third application is in stereochemistry. I use a very simple one, cyclopentadiene plus maleic anhydride. You can get two stereoisomers. If you isolate a product, forget it's this simple. If you've isolated a product, you'll get an NMR. You can now sketch all the possibilities here and ask the question, what am I actually seeing? So these are tasks that can become completely routine, is the word I want to emphasize. I've said this on two slides. Most molecules are flexible, and the NMR, because it's a slow experiment, is an average, as opposed to, say, infrared, which is a superposition. So what this means is that what you're observing, at least at normal temperatures, is a weighted average of different conformers. Conformational flexibility is a much faster process than the physics underlying NMR, nuclear relaxation. And so what you have to know is not only the NMR spectra of the individual conformers, but how much they contribute. The jargon are Boltzmann weights, which is basically just the function of the energy and the temperature. If you think about this, you can apply the same automated procedure as one used for conformational analysis, but add a single step at the end, which is to treat the conformer energies as indicators of the Boltzmann weights, and then to take all the weights up to, say, 99% or 95% or 90 or whatever you want, and simply compute the NMR spectrum and then multiply the two together. You'll now get a weighted spectrum. This process is fully automated in the sense that you take a molecule, build it any way you like. You throw it essentially through the procedure that calculates a conformer distribution, which is the same thing as the Boltzmann weight. You then select, and this is all automatic again, you then select the ones that count. So you have to put in a cutoff, or the program puts in a cutoff, and you multiply the two together. You never really have to deal with the individual spectrum, and what you get is an average spectrum. Pretty simple. One step, again, significant computer time, depending on how many conformers it has and how complicated the molecule is, but the process is very simple in human time. Nice collaboration with a gentleman in this room, started too long ago, was to test this with selection of natural products. This started out rather modest. I think we originally agreed on we'll do 300. It's now up to 2,300. And those natural products we put into two categories, two buckets. The first bucket is actually about 850 molecules that have crystal structures or have been synthesized. What I mean by that is that their structure is pretty much unambiguous. They range in molecular weight. There are a few of them that are really tiny, and the biggest ones are something like 700 AMU. So they're reasonable sized molecules. They're not huge. If you look at the blue curve are the ones that are about 850 now, natural products that are crystallographically known or synthetically known. And if you look at the blue bars, you'll see you get a pretty clean histogram, and past about 3.5 ppm, this is the RMS error, there are none. One can see here that the method is producing that's roughly, the RMS would be roughly here. It's roughly 2 ppm, which was our stated goal. There are a couple of blue outliers. I think the worst one is actually here. Those outliers are, I think we've concluded with one exception, which is a molecule I don't want to discuss, that they're all due to peak misassignments. So it's pretty innocent. The structure's right, but the NMR has been incorrectly assigned. Here are 2 examples. They're almost always quaternary carbons, which are presumably harder to go after than ones with hydrogens attached. So you can see if you correct for these, actually that curve gets somewhat better. Now, if you look at the remaining set, it's about 1,450 actually molecules where the structure assignments are solely by NMR. Now that's a little dishonest. You also have mass spectrometry in there, and you also have experience, biology, previous chemistry, lots of other things. Let's say solely by NMR to make my life simple. Those are the red lines. And you can see there, the histogram is shifted, but I don't care so much about that. There's a lot of junk out there. And if you actually integrate over that, it's about a little less than 10%, which are outside the bounds of innocence. Being polite, they're wrong. Now, they may be wrong for several reasons. They may be wrong because of peak misassignments. There are a few like that. All these are innocent, conspicuous peak misassignment. They may be wrong, but not really wrong because of an incorrect tautomer. This is a cute one, actually. You can't really blame anyone. It's just a different tautomer, but their NMR is quite different. This one has an RMS of 10 ppm, which is outside the limits of reasonableness. And if you just shift tautomers, you're down to 2 ppm. Here's actually my favorite one because this one's really annoying. This is one of the earliest ones we did. And here's the original structure. So, what I've plotted are differences between calculated and experimental shifts. And this one's trash. You're off by 30 ppm. That's impossible. And you're off by 10. It's wrong. It turns out that this spectrum is identical to an existent molecule panacene. And what makes it interesting, this is a perfect fit. What makes it interesting is the molecular weights are different. It differs by BR2. And so here, not only is the NMR screwed up, the mass spectrum is screwed up. Again, innocent. I know there are many examples of this. I don't really want to go into that. We've put up data set on a browser. Chrome is the best one to use. We basically put a library of the compounds, and given that it's a web addressable, this library will be constantly updated. And basically, it contains the 2,300 compounds under a name, under a reference, and they're up through. It's pretty current. It's not every molecule that's published. It contains the name of the first author and then the error statistics. And so you can sort and find a bad one or find a good one. And when you look at them, I've just picked some random object here. When you look at them, you can see plotted on a picture these are the deviations between calculated and experimental, or you can see either the experimental or calculated. So this is a library. It's under nmr.wayfund.com. Okay. I guess my final slide. What are we doing now? We're doing some interesting things at this point. We're trying to build a density functional model for NMR chemical shifts. As I said before, these are models that have certain expressions in them, and they have lots of parameters. And they've all been parameterized to fitting energy data. The other large data set available in chemistry is NMR data. And so we're now involved in trying to build a functional which is specifically trying to get chemical shifts. It will probably do terrible in getting energies, but I don't care. It's trying to get NMR shifts. That's one project. Another one is taking another look at very simple molecular mechanics, or very simple models for conformational analysis. I've convinced myself that present generation molecular mechanics is not very good. But there's another approach, and that is to start from there and to correct it with a neural net kind of model, which is really a nonlinear optimization. And so we're playing with this. This is a long shot. Another general area is we're combining. We have a large database of normal molecules, about 300,000, and we have a smaller database of a couple of thousand transition states. We're going to combine those two so they can be basically used interchangeably. Where if you build a transition state or a reactant, it can. If you build a transition state, it can go back to the reactant, forward to the product, and do it in one shot rather than having to do things independently. The other thing we're doing is we're recognizing that the computer world is going in a direction which is not making things faster, but making things multiple. The chip speeds have not reached their limits, but they've probably come fairly close to that now, at least for silicon technology. And what you see happening in industry is that the chips are getting more and more processors. The current record, I think, is an AMD chip, which is 32 cores. I fully expect that's going to double in a year or two and double again in a year or two after that. So that's the direction. Making chips, once you've actually got the design, is photography. The hard part is trying to couple these things together. And at some point, you've reached a high enough number that the algorithms will not parallelize, but I think we can probably go up to maybe 100 processors. So what that means is something that takes 100 seconds now will take 1 second in a year, 2 years, who knows. So that's all I'm going to say, and I'll open it up.